Okay, this topic is a little bit complex. Let's talk about probabilities, proportions, and p-values. We'll start with probabilities, proportions, and percentages and come to p-values later. So what's the difference between these three things? Well, probability is the chance that something will happen. It's expressed as a number that can range from 0, meaning no chance, to 1, meaning that something is certain to happen. So for example, a probability of 0.5 means that there's a 50-50 chance that an event will happen. A proportion, on the other hand, is a fraction expressed as numerator over denominator. And a percentage is also a fraction, but with 100 as the denominator. So for example, the proportion 4 over 5 equals 80%. So again, probability is the chance. You can also think of it as a risk or a likelihood of something happening, always between 0 and 1. We talk about simple probability, which is the probability that one thing will happen. The probability of A is written P of A. So for example, what's the probability that a flipped coin will land heads up? What's the probability that a rolled die, just one dice, will land on a number greater than 3? Now, a conditional probability is the probability of one event, A, given that another event has occurred. So we write this, the probability of A given B is the probability of A and B. You can visualize this in terms of set theory or overlapping Venn diagrams. What's important here is to distinguish conditional versus independent events. So when are events really conditional, really dependent on each other, and when are they not? And one way to think about this is to think about the question, what's the probability of a flipped coin, that a flipped coin will land heads up, given that the last coin flip also landed heads up? What's the answer? Well, the answer is 0.5, because a flipped coin does not depend on what happened before. Not at all. But if you're talking about, so flipped coins are independent events. If you're talking about rolling a dice and you're going to roll 2 dice and you're asking what's the probability of getting a total of 12, then the result is conditional on getting a 6 for one die and a 6 on the other. So here the question is, do the events really depend on each other or not? So percentages are based on observed data, and they're useful for expressing rates, proportions, and for comparing groups. But percentages are often badly misunderstood, as in this cartoon. Here's why it matters. We use percentages to understand lots of patterns in our world. So for example, the map on the left shows the share of the population with mental health and substance use disorders in 2016 in various countries. And when you look at this map, it is clear that rates of mental illness and substance use are high in the US and Australia, for example. And then if you take a look over on the right, another map showing what proportion mental health and substance use disorders are as a share of the total disease burden in the same year, you see that again in the US and Australia, mental health and substance use disorders take up a large proportion, relatively large proportion, of all disease. And that makes sense because there are other diseases that are much more common, particularly in sub-Saharan Africa and South Asia, communicable diseases and so on. So all of this is communicating a lot of information just using percents. Now the quality of data matters as well. So on the left you see a map showing suicide death rates per 100,000 people in 2016. And it appears that suicide rates are very high in Greenland. Then on the right, there's another map showing the quality of suicide mortality data by country. And here you see that for Greenland, the data are not reliably available. So it's a mistake to conclude that suicide death rates are high in Greenland if the data are not reliably available. Let's talk about percentages, change, and base rates. This is where a lot of people get confused about percentages. When we talk about the percent change, that refers to a difference, an increase or decrease. And it's very difficult to evaluate unless we have information on the base rate or the starting point. So we're comparing a percentage at the beginning with a change leading to another percentage at the end. So for example, a 50% increase sounds like a lot. It means something is increasing by half. But what it really means, the magnitude of this change, depends on the base rate, the starting point. So if the base rate is 2%, a 50% increase means that we're going to add half of 2%, or we're going to have a net increase of 1%, and that will bring us to 3%. If the base rate is 30%, a 50% increase means that we add half of 30%, or a net increase of 15%, and that brings us to 45%. If the base rate is 60%, a 50% increase gets us to what? What's the answer? Well, the answer is 90%. And here on the left are the 50% increases that I just mentioned. And decreases work the same way. The amount that it's going down depends on the starting point, the base rate. So often we have partial instead of full information, which can be very hard to evaluate. So here on the left, we have a graphic reported by child trends showing changes in cocaine, heroin, and methamphetamine use among high schoolers from either 1991 or 1999 to 2017. And they show, decreases in the percentage of high schoolers using these substances. But on the right, I've basically rescaled the data, showing original data. So originally, cocaine use in 1991 was identified in almost 6% of the youth, and it dropped to about 5%. In contrast, heroin use in 1999 was around 2.4%, and it dropped to 1.7%. And then methamphetamine use at 9% in 1999 dropped to 2.5% in 2017. So this gives you the full picture on rates of use before and after, and you can see the percent change. It's much better information. It's full information. So it's important to get the scale right. Okay? I've taken the same data on the right, and instead of blowing them up the way many people would do, I've put them on a scale of 100% for all youth. So you see, when you get the scale right, we are concerned, of course, about use of these kinds of substances, but this picture shows you that most high schoolers are not using cocaine, heroin, or methamphetamine. Here's some other reasons why it matters. So understanding trends in poverty over time. On the left, you see the percentage of change in children in poverty. So this is a percent change that does not give us a base rate. But here on the right, we find the results. So what percentage of children under age 18 are living in poverty in various U.S. counties in the year 2016. So both kinds of information are useful, change and raw percent. I want to shift now to talk a little bit about what we can do with probabilities. One of the things we do is we use probability for creating samples. These are called random samples, and we use them to estimate population parameters, or the averages or proportions of something in a large population. So the way we do this, and we're going to talk about this more completely later on in the semester, the way we do this is we take a target population and we take a random sample of that population, and that sample generates some statistics. So here I'm illustrating 3 different random samples that give us 3 different statistics. In this case, these are averages, which are represented by the letter X with a bar over it. That means average. So we get 3 different statistics. Okay, random samples from the same population will be a little bit different. There are going to be different people in each of these samples, so they'll produce slightly different statistics. Another way to go about this is to stratify the target population, or divide them into strata or homogeneous groups, and then take random samples from each stratum. So stratified random samples sort samples into important subgroups and assure that each subgroup will be adequately represented in the sample. Probability theory, which is going to be very important for lots of reasons in this class, suggests that statistics from random samples of the same population, statistics from those samples, are distributed in a normal curve around the population parameter. Okay, so here we see a normal curve, and 0 is the mean, the average of that curve, and the statistics from these 3 samples are going to be somewhere within that curve. We use standard errors to describe the area under the curve, and we know from probability theory that 68% of all samples will generate statistics within 1 standard error of the population parameter, and 95% of all random samples will generate statistics that are within 2 standard errors of the population parameter, and 99.7% of all random samples will generate statistics that are within 3 standard errors of the population parameter. That's one main aspect of probability theory. Okay, so we're going to use the 2 standard errors. Statistics from 90% of all random samples will fall within, that is plus or minus, 2 standard errors, about approximately 2 standard errors of the population parameter. This is where our confidence intervals come from. So we can say that we're going to be 95% confident that a statistic from a random sample will fall within, plus or minus, 2 standard errors of the population parameter. So what is a confidence interval? Again, I'm repeating this statement. We are 95% confident that a statistic from a random sample will fall within approximately 2 standard errors of the population parameter. We use this logic to create a confidence interval around a sample statistic, and this expresses the level of uncertainty we have about a statistical estimate. So here I'm showing in a blue line with arrows on either end a 95% confidence interval around a population parameter. And remember, the population parameter, the characteristic of the population, is in the center of this distribution of sample statistics. But we don't, oh, and here's our sample statistic. It could be anywhere in this distribution, but just for purposes of illustration, I put it where the blue dot is. Now the problem is that we don't know where the population parameter is. All we know is what our sample statistic is. So we redraw the 95% confidence interval. Instead of it being in the middle of the distribution, we draw it around our sample statistic. And now we flip the logic and we say that if 95% of all samples will generate statistics that are within 2 standard errors of the population parameter, then the population parameter has to be within 2 standard errors of our sample statistic 95% of the time. You might need to replay this a little bit. This is complicated. It's complex logic, and it's really important for understanding essential inferential statistics. So the confidence interval relates to the margin of error that we read about in relation to opinion polls. Sample statistics provide an estimate of the population parameter, the characteristic in the population, and the margin of error is half of the 95% confidence interval. Sample size affects the precision of these estimates. so that larger samples have smaller confidence intervals. Larger samples give us more data. We're more certain that the results are going to be close to the population parameter, and smaller samples have more variation, more error. So larger samples provide statistics that are more precise estimates closer to the population parameter. So you see here, let's say this is an opinion poll where 50% agreement is somewhere in the middle. You can see the sample sizes needed to get different margins of error. To get a 2% margin of error, which is a pretty precise estimate, we'd need a sample of more than 2,400 people. To get a 3% margin of error, a wider estimate, we need a smaller sample. So 95% confidence intervals, which are the intervals we usually use in statistics and research design, mean that a confidence interval indicates the level of uncertainty around a statistical estimate. Larger confidence intervals show more uncertainty, less precision. Smaller confidence intervals show less uncertainty. So now we're talking about the precision of an estimate. An estimate is information gathered from a sample. So here's a question for you. Which of the following estimates is least precise? If we say the average in a sample is 50 with a 95% confidence interval of 48 to 52, or an average of 20 with a confidence interval 18 to 22, average of 10 with a confidence interval of 5 to 15. Which is the least precise? How do you figure this out? Well, you figure out the margin of error. Confidence interval of 5 to 15 is a total of 10. The margin of error is 5. Confidence interval of 18 to 22 is a difference of 4. Margin of error is 2. The confidence interval of 48 to 52, also a difference of 4. Margin of error of 2. So the average with the largest confidence interval, or margin of error, is C. So thinking about probability theory and p-values, we use probability theory to estimate the likelihood of a specific observation, and this gets us to p-values. The p-value is the probability of an observed result given certain assumptions like random sampling. So if we find a result that's likely to be in the middle of a distribution, that's not surprising. Finding something that's extreme, either positive or negative, is surprising, and the probability that we will find a result like that is very low. So let's say we have an observed data point. Now it's this red dot, and we could have received any kind of result in this sampling distribution, but we got that result. The more likely observations are in the middle. The very unlikely observations are in the tails of the distribution. And our p-value is the shaded green area that represents the probability of an observed data point like the one we had, or one more extreme, assuming that the null hypothesis is true. The null hypothesis is that there really is no difference or no result. We'll talk about that more in a little while. So what is a p-value again? A p-value is the probability of obtaining a specific result, or one more extreme, from a random sample. Using our current conventions, p is less than 0.05 is used to indicate that the result is statistically significant. Again, this is a convention. It is somewhat arbitrary, but this is a very common rule in research. A p, or a probability greater than 0.05, indicates that the result is not statistically significant. It's something we would expect to find. It's not unusual. So what's in a p-value? For one thing, the term statistically significant in research does not mean important. A p-value, a statistically significant p-value, means it's highly unlikely. A p-value does not prove whether a hypothesis is true, and more statistical tests are not better. More questions and larger data sets actually increase the likelihood of p-value mistakes called type 1 errors. It's also important to note that the absence of evidence, if we find there is no significant difference, is not the same thing as evidence of nothing, evidence of an absence of a difference. So not significant does not mean no difference. It means we didn't find a difference this time. Some p-values are deliberately hidden, and this is called outcome reporting bias, which we'll talk about more later. And it means that p-values that are less than 0.05 are more likely to be reported, because they're called statistically significant, than p-values that are greater than 0.05. And that is reporting bias on the part of researchers and to a lesser extent on the part of some journals. Okay, that's all for now. I'm sure